Okay, it looks like it's time for us to start. Have we let everybody in? Okay, let me welcome everybody today to our CASIRAS LSTC seminar, the webinars that we've been doing periodically. We are really excited to have a great guest today. This is sponsored by CASIRAS, the Center for the Advanced Studies of Religion and Science, by Lutheran School of Theology, and also through the Zygon Center for Religion and Science as well. I now want to introduce to you Grace Wolf Chase, the Vice President of CASIRAS, and she will introduce our speaker for us. Grace.
Thank you, Gail. So I am delighted to introduce today's CASIRAS speaker, Dr. Heidi Hammel. Dr. Hammel holds an undergraduate degree from MIT and a PhD in physics and astronomy from the University of Hawaii. After a postdoctoral position at NASA's Jet Propulsion Laboratory, she returned to MIT as a principal research scientist in the Department of Earth, Atmospheric, and Planetary Sciences. And her primary research interests focus on the outer planets of our solar system. Dr. Hammel has been involved in many NASA missions and observatories, such as serving on the imaging team for the Voyager 2 Neptune encounter in 1989, and leading the Hubble team that studied the impact of comet Shoemaker-Levy 9 with Jupiter in 1994. In 1996, Dr. Hammel received the Urey Prize from the American Astronomical Society for her outstanding achievement in planetary science. And in 2020, she was awarded the Mazursky Award for her service to the planetary science community. In addition to being a distinguished research scientist, Dr. Hammel is an award-winning science communicator. She's received the Public Understanding of Science Award from the Exploratorium in San Francisco, and she was the 5th person ever to receive the Carl Sagan Medal for Excellence in Public Communication. So as a side note, together with David Grinspoon and Guy Consolmagno, Dr. Hammel is the 3rd speaker in our webinar series to have received this prestigious award. She's currently the Vice President for Science at the Association of Universities for Research in Astronomy, a consortium that operates world-class ground and space-based astronomical observatories. She's also an interdisciplinary scientist with the James Webb Space Telescope, where her focus is on planetary systems and the origins of life. As some of you may know, the JWST, originally scheduled for launch in 2007, is scheduled for launch later this month. One of the positive aspects of the 14-year delay is that the telescope is now better positioned for the study of potentially habitable conditions on exoplanets. Dr. Hammel is exceptionally well qualified to tell us about JWST science priorities, and I, for one, am also very curious to hear her response to the question posed to her in a recent interview: will the James Webb Telescope see God? Take it away, Heidi.
Thank you very much, Grace. Let me start to share my screen here. And let's see, we'll put this in a viewing mode so you can all see it. Yeah, this question was posed to me in a recent interview with the BBC after a really standard, normal, what are you going to do with Webb? Tell me about what you think. He said, oh yeah, and my aunt's really excited about James Webb Space Telescope because she thinks it's going to find God. Will James Webb Space Telescope see God? And that was a pretty interesting question. And I'll tell you at the end what my answer to this is. But here's the outline of what we're going to cover in today's talk. First of all, I'm going to talk about what is the James Webb Space Telescope for those of you who are not familiar with it. And we'll talk about how does Webb see things? What does it even mean to see with Webb? I'll talk about what we plan to observe with Webb Telescope. And then at the end, I'll talk about will Webb see God? Okay, so let's talk about what is James Webb Space Telescope. Here is a picture, an artist's concept of what Webb looks like. It's a really different kind of telescope. It is very large, covered in gold, no tube enclosing the telescope itself, a very different kind of telescope than the Hubble Space Telescope. And many of you have, I'm sure, have heard of the Hubble Space Telescope. And this is a picture of what Hubble looks like. And Hubble has been our workhorse space telescope. It's not the only space telescope, but it's been one of the most productive space telescopes in the history of humanity. And it's still doing great science right now. So I thought I'd sort of use it as a comparison, like, why are we building another space telescope? Why is Webb different from Hubble? And so there's basically 4 things I want you to remember about how Webb is different from Hubble. And the 4 things are that it's bigger, it sees redder, it's colder, and it's further. And all of those 4 things are crucially important for the key science that we want to do with Webb. So what do I mean by bigger, redder, colder, and further? So let's talk about bigger, first of all. Here's a cartoon showing you the 2 telescopes to scale with the small human being person who just disappeared, and he's back. And the key component of a telescope, the thing that we call the size of the telescope, is the mirror. That's what we use to collect the light from the cosmos for our telescope. And for the Hubble Space Telescope, the silver mirror that you see there on the right is 2.4 meters across. The Webb's mirror, in comparison, is 6.5 meters. In more human terms, that's like 21 feet across. So that effective area of that telescope is so much bigger that we get more light from the cosmos. So we can see fainter and further things. And so when I say bigger, that's what I mean. It's in fact so big that it doesn't fit inside the standard rockets that we have to get it up into space. And the cartoon of the rocket on the side, that's a picture of the Ariane 5 rocket where from which Webb will be launched. And you can see up in the very top what we call the fairing. You can see the telescope all folded up inside there. The large picture is an actual picture of James Webb Space Telescope all folded up in its launch configuration just before it left California, where it was finally assembled, before it was sent off to the spaceport in French Guiana via boat. It took a long boat ride through the Panama Canal to get to French Guiana. And we're launching from French Guiana instead of Kennedy or Canaveral in America, because we're launching on a European Space Agency rocket, the Ariane 5. That was a donation from Ariane. The Ariane rocket was given to us as part of the contribution from the European Space Agency. This is not just a NASA mission. NASA's the lead, but we have contributions from the European Space Agency, the rocket, and also one of the instruments, and also the Canadian Space Agency, which contributed another instrument, including our fine guidance sensors for this telescope, multinational. So once we launch this thing, we have to unfold it. And so here's a video that shows you some of the steps. This is all going to take place in the 30 days it takes to get from our launch up to its location in space at a place called the Lagrange 2 point. And you can see that there are many things happening. You can see that what's unfolding here off to the side is 1/2 of the sun shield. I'm going to now speed this up a little bit. Make it a little faster. You can see the other half of the sun shield unfolding, and then it separates into 5 distinct layers. And this sun shield keeps us cold. We'll get to that. And then we have to unfold the mirrors itself to make the final telescope. And this process takes about a month for this all to happen. It's going to be it's going to be a very nerve-wracking month of January for us watching that all take place. Okay, so we talked about it being bigger, and now let's talk about redder. What do I mean by redder? I mean, we're going to see redder wavelengths of light. So let me talk about light just for a second here so we're all on the same page. Isaac Newton did an experiment where he put a prism in a little hole in the wall, and the sunlight was spread out into a rainbow of colors. And we call this the rainbow. We call it a spectrum. But what's important for us in astronomy is that the light from the cosmos, from astronomical objects and from everything really, it doesn't end at red or blue at the opposite ends of the spectrum. Light keeps on going to even longer wavelengths, redder, or shorter wavelengths, bluer. And you've heard of these other kinds of light. They have names like radio, microwave, infrared, UV, X-rays, gamma rays. You've heard those words. Those are all light. Those are all different kinds of light. And this is important for astronomy because the universe emits light at all of these wavelengths. So we want telescopes that cover that full electromagnetic spectrum. And you might say, well, great, why don't you just build telescopes all over the ground? Why do you have to put them in space? Well, the answer is that Earth has an atmosphere, and our Earth's atmosphere actually absorbs light at certain wavelengths. And in fact, pretty much all of the wavelengths that are shorter than visible are absorbed by Earth's atmosphere. And the light from the universe never makes it to the surface of the Earth. So if we want to see that light, we have to put our telescopes up in outer space. When we go longward, there's a big chunk of infrared and microwave light that doesn't make it to the ground. Radio does. That's why we have a lot of big radio telescopes on Earth. But basically, optical, visible wavelengths, and radio is all that gets to the surface. And so to see the infrared, we really have to go to outer space. And that's why we're putting James Webb out there. So why? What's important about that infrared light? Why do we care? Why not just use Hubble? Why not just make a bigger Hubble? We do want to do that. But there's a really important science reason we want to go out into the infrared. Two really important science reasons. First of all, visible light has some limitations. And those of you who have ever explored things with thermal cameras, you know what those limitations are. Here's a guy holding a bag, and I'm pointing over here because I've got a big screen here where I can see what you are seeing. He's holding this garbage bag over his arm, and you can't see his arm. You know it's in there, right? But you can't see it because that garbage bag is opaque to visible wavelengths of light. You just can't see it. But if you had an infrared camera and took a picture, you could see right through the bag, and you could see his arm inside the bag because the infrared light is transmitted right through that garbage bag. Okay. And this works in space too, the same principle. Here's a constellation that many people are familiar with. It's the Orion constellation. And he's got like the 3 stars or his belt. He's got a little sword hanging off it, and he's got a nebula on it. But this is visible light. And if we put an infrared camera onto the sky, what you see is that it looks dark in many places because there's a lot of dust in this area. And in fact, this is an infrared image of the Orion Nebula, where you can see that the bright thing that is just barely visible to our visible wavelengths is really, in fact, a bright opening into a very large dust cloud. You need the infrared light to see through this dust and detect things. And this is important in astronomy because where stars are born and where planets are born are enshrouded in dust. So to actually see star formation and planet formation, we have to be able to look in the infrared through the dust. So that's one important reason. A second important reason that we want to look in the infrared is that we're interested in exploring the very first stars and galaxies that ever emerged in our universe. And there's a very interesting principle that we've learned about over the decades called cosmological redshift. So here's an example of a spectrum of light, and there are certain characteristic lines of light missing here, and that is due to absorption by certain molecules in the cosmos, hydrogen in this case, a nearby star, and you can see those lines. We label them with the Greek alphabet. But if you look at a nearby galaxy, which is mostly starlight, if you look real carefully, you can see that the lines are shifted just a little bit to the red. And if you look at a very distant galaxy, that shift is obvious. I mean, just look at the epsilon line moving off to the red. And if you look at really, really, really distant objects, like the first galaxies ever formed, it's shifted so far into the red that it's moved out of the visible and into the infrared. And this has to do with the expansion of the universe. It's getting larger and larger. As it expands, the wavelengths of light expand, and longer wavelengths are redder wavelengths. And you can see this in Hubble images. All these spots here are extremely distant galaxies in the Hubble deep field, and they're all red, you know, they're red. So if we want to see these early galaxies and actually see ones even earlier than these, we must go to the red. And another important property about infrared light is that it is essentially the same thing as heat. It's warmth. And so you build a telescope that you can see things that are warm, you have to have your telescope cold, because if your telescope is warm, all you're going to see is your telescope, and it's infrared radiation. So you have to have your telescope super, super cold. And that's why I say that Webb is colder than Hubble. And when I say cold, I don't just mean like, oh, I'm feeling cold right now. I'm talking about cold. 50 Kelvin, that's minus 370 degrees Fahrenheit, minus 223 degrees Kelvin, if you prefer that unit of temperature. This is the cold of space. And in fact, it's actually colder than the cold of space. So we have coolers on the telescope that take our instruments and make them even colder than the ambient space around them. And we do that so that we can sense the faint warmth of the distant galaxies and stars and planets and objects in our solar system. And so how do we mostly keep it that cold? Well, the same way you keep cool when you're on a beach. You've got a beach umbrella that blocks the sun. Well, those big shiny pink things that I have Webb upside down here, because they are our umbrella, they protect us from the sun and they keep us cooler. From one side or the other, the temperature can drop hundreds of degrees of Fahrenheit. Another way of thinking about this is, you're familiar with sunscreen and the sun protection factor, SPF. And, you know, the most powerful one I usually use is 50. You can even buy up to 100. Our sun shield on the James Webb Space Telescope has an SPF of about 1.5 million. That's how much of the sunlight we cut out using this. And finally, we're bigger, we're redder, we're colder, and we're further. We are not in low Earth orbit like Hubble Space Telescope. And the reason is Earth is warm, the moon is warm, the sun is warm. So we are sending our telescope away from the Earth, far away from the Earth, 1.5 million kilometers. That's like 1 million miles away from the Earth, in a special place called L2. If you drew a line, as you can see here, from the sun to the Earth, and then keep going in a straight line for about 1.5 million kilometers, 1 million miles, that's the L2 point. It's a gravitationally stable point. And we're going to put Hubble in a little tiny orbit there. And while it's in that orbit, its sun shield will always be between the telescope and the sun, Earth, and the moon. All right, so that's the orientation. So that's what Webb is. How does it see? Like, a lot of times people think, when they know I'm an astronomer, they have this idea in their head. They say, can I see your telescope? I want to look through your telescope. If you Google looking through a telescope, this is what you see. It's all these people with their eyes peered to eyepieces on little small telescopes. Professional astronomers haven't done this for a century. This is not what we do. Everything that we do is done with computers. A century ago, it was photographic plates, but about 40 years ago, we transferred to electronic cameras and electronic sensors. So everything now is done electronically, and we don't do this. I don't look through a telescope with an eyepiece, which is good because this telescope's out in outer space. So you can't look through it anyway, right? Because I'm not an astronaut, I'm an astronomer. So here's a picture of me working at one of the largest telescopes in the world. I'm the person sitting over on the right, and you can see my multiple screens in front of me showing me my scientific instruments. The guy over on the left is the telescope operator. He runs the giant telescope that we're using. There's a screen in the middle, which is one of my collaborators who could be anywhere in the world. We don't actually even work at our telescopes anymore. Everything is done remotely. So this is how modern astronomy is done. And so it doesn't matter to me that my telescope is 1 million miles away. They'll just be sending radio signals to the telescope, telling it what to do. It'll radio the data back to the Earth, to the Space Telescope Science Institute, and that data will be put into a science archive where I will get it and work with it on my computer here in my office, currently in my basement of my home in Virginia. All right, so what do our cameras look like? When I say camera, I am not talking about like a camera on your phone or a 35mm camera or anything like that. This picture on the left shows you what our camera instrument suite looks like. And there's a person there for scale. And you can see that it's big. We have 4 different instruments. We call them instruments. That really means equipment, cameras, and spectrographs. We have 4 different instruments on Webb to use to look at various types of colors of light and different ways of looking at the light. And the picture on the right shows you that instrument package being lowered on a crane onto the back of the telescope. That's where it sits, is on the back of the telescope. You can see the telescope upside down underneath it in that picture. So these are the tools we use to see things with the James Webb Telescope. We use cameras and spectrographs. So what do we plan to see? I have a little video that I put together to sort of take you through some of the kinds of science that we are planning to do with James Webb Space Telescope. And so it's called a scientific exploration with Webb. We launch Webb in the 22nd of December, coming up real soon. The first thing we're going to do, our primary science, is we're going to see the first light in the universe. This picture video is from the Hubble Deep Field, taking you all the way back close to the Big Bang. We don't see the Big Bang. What we want to see is the galaxies and maybe the stars that formed right after the Big Bang. So the very first light. And then once we see that first light, we actually want to see how those first galaxies and stars interact with one another to form the galaxies we see today. We know that galaxies interact, like in this simulation on a computer, but we want to see how they come to form the beautiful spirals that we see today. And then in our local galaxy, we want to dive into the dusty areas where we know stars are being born. And by looking at our infrared wavelengths, we can peer through the dust and actually see not only those stars, but even the planetary systems forming around those stars. So it's crucial for us. And then once we know of almost 5,000 planets around other stars, a huge diversity, some like our world, some not like our world. We want to probe their atmospheres to truly understand what's there. And we do that by looking at light that comes through the atmosphere, and we look at the characteristic signatures, fingerprints of light that are taken away. Here's a fingerprint of a planet, and this planet has a blue sky. It has signs of vegetation, it has water clouds, and it even has methane that we know comes from animals. That was Earth's atmosphere. That's the kind of thing we're looking for. Then we will be flying through our solar, we will not be flying, we will be looking at objects in our solar system to try to understand the chemical constituents of everything in our solar system. And so it's a huge voyage of discovery with Webb. Everything from the most distant stars to the nearby asteroids in our solar system. That's what we plan to study. And so, as I said, the first light, the first galaxies, the assembly of the galaxies, how stars and planetary systems born, and then characterizing planetary systems themselves, searching for the origins of life elsewhere. This is the science that we expect to do, that we have been planning for 20 years to do. But I will share with you my experience with Hubble is that you don't know what's going to happen. We don't know what's going to happen. And sometimes the unexpected science is the most interesting. So I don't really know yet what the most interesting and unexpected science is going to be in these 4 themes that we've outlined for Webb. And more importantly, I bet that there's going to be a whole lot of other science that our teams haven't even thought of yet, but some clever young whippersnapper is going to come along and say, you know what, with Webb's sensitivity and infrared capability, I'll be able to X, and I don't know what X is, but X could change our view of the universe. And that's what's really exciting about a big telescope like Webb, is that we just don't know what we are going to see. We have our ideas and our plans, but there will be surprises. So let's turn to that final question. Will Webb see God? All right, so I'm going to be a little flippant here, and I'm going to tell you, first of all, the things I'm pretty sure we're not going to see with Webb. I'm pretty sure that when we turn Webb on and start doing science, we are not going to see a big guy in the sky with a long beard and white hair. We're not going to see God like this in the sky, okay? It's just not going to happen, right? I'm sure of that. That's not what we're going to see. And I also want to share with you something that has been making the rounds on the internet for a while now. This picture, people say, oh my Lord, the Hubble Space Telescope has taken a picture of the city of God. I call this Heaven's Gate. And you know what? No. This, first of all, this picture is a distortion. It's an art piece that was created by someone based on an image that was not taken by Hubble even. It was a very large telescope called the VLT, very large telescope, which is in Chile. And this artist, part of his ethos is distorting reality in ways, not just astronomical pictures, but other pictures. And so he took this beautiful Swan Nebula picture taken with the VLT, and he distorted it in this way. And you can go and look at his art. I put the website there if you're interested in exploring other things that he's done. But no, we will not see the city of God. All right, this is those things. That's pretty sure. So like this question, you know, will Webb see God? How does one even see God? What does that even mean? Like how? And even if you can you see God? I mean, I don't mean, what does that even mean to see God? Are these even reasonable questions to ask? And in particular, are they reasonable to ask an astronomer? I mean, we got a whole lot of theologians there at LSTC. Maybe we should be asking them, how do you see God? So I'm going to sort of reflect this question back to my listeners. How do you see God? What does it mean to see God? Do you see God in the land around you? Is this great creation of ours? Is that to you, when you see that, is that how you see God? And if that question for you, if the answer to that is yes, then Webb is going to reveal cosmic landscapes, vast and ethereal, that we haven't yet seen before. We'll be seeing a new aspect of God with Webb, if that is how you see God in that to you. Do you see God in the waters? Is the waters that have formed our world and that surround us, that give us life, that, you know, was the basis of baptism, that was turned into wine? Are the waters, is that for you? Is that how you see God? If the water is, if that is your perception of how God manifests, then we will be seeing cosmic oceans of gas and dust. This image from the Hubble Space Telescope, I think, is one of the most evocative Hubble images I've ever seen. It's in the heart of the Crab Nebula. And in the heart of the Crab Nebula, there is a star that is pulsing. And as it pulses, it sends ripples out into the gas and dust, just as we see ripples in water here on Earth. And so I just, when I see this image, it really takes my mind to a very different place. Is that how you experience God? Maybe it is. Or maybe you see God in the patterns of nature. You say, you know what? It's impossible to imagine that nature would just naturally have the same shapes and patterns and styles, whether you're talking about a snail shell or a fiddlehead fern or a hurricane or a succulent leaf, that concept that this cannot be random. There has to be something behind this. And that something is the sign of a higher purpose. And that's God manifesting in nature. If that is how God manifests for you, then Webb will take us even further down that path, because these same patterns that we see here on Earth in animals and in plants and in crystals and in weather systems, we see them all throughout the cosmos. Here's just 3 examples of beautiful spiral patterns, just as we were seeing in the previous slide. Maybe though, for you, God is people, and how people interact with one another, and how people care for one another and work together and speak to one another. And maybe that is to you how God is manifest. And if that is the case, then I would share with you that this telescope, which is a thing, this thing didn't just emerge out of nothing. This thing emerged out of the minds of people who had passion and desire to learn more about the universe around them, and worked together as teams, whether it was teams working on the mirror, teams working on the sun shields, teams working to make sure everything was aligned. Here's a picture of me and the person who's working with me, Stephanie. And that picture in the middle, that's just a tiny subset of the thousands of people who have worked to make James Webb Space Telescope a reality. If to you God is manifest in how people come together to fulfill a dream that is something that is positive in the world and will only add joy, wonder, and beauty to the world, if that's how you view a manifestation of God, then we are there. This is it. This web is a product of the combined joy and passion of thousands of individuals all across the globe, working together to realize this vision, to see deeper into the cosmos. And then I just wanted to let some of the pictures speak for themselves. The psalmist, Psalm 19 said, "The heavens declare the glory of God. The skies proclaim the work of his hands." And just Hubble alone has sent us remarkable views of the heavens, and they are articulating that work, whether it's just fields of stars, beautiful images like this, which are a star that is throwing off multiple jets and shells of dusty material around it, whether it's a beautiful barred spiral galaxy that's just filled with stars and dust, and every one of those stars has planets around it, or whether it's a cluster of galaxies. Each golden smudge that you see in that picture is a galaxy composed of billions of stars, and every one of those stars almost certainly has a planetary system around it. The cosmos is not, it's not infinite, it's finite, but it is all there for us to explore, to expand our knowledge, and to glory in. And so if these are truly manifesting the works of God, to me, this is just an opportunity for us to peer deeper and further and more joyfully into the universe. So that's what James Webb is all about. I wanted to share one last picture with you. Many of you have seen this, the image on the right, on the left. It's called the Pillars of Creation. It's a part of a nebula called the Eagle Nebula, and it's a place where stars are being born. And we know that, and we want to see that in greater detail. And the picture that you see on the right is an infrared picture taken with a telescope on the Earth. And you can see, as I said before, we see through that dust. We see stars that are invisible to us in our visible wavelength Hubble image. This will be one of the targets of Webb for sure. It will be a better picture than this. It'll be a higher resolution image, higher resolution than this. And we will be able to probe the tips of those pillars where stars are being born, planets are being born. It's going to be really remarkable. And this all launches days from now. We're counting days now. It's really exciting. Someone who's been working on this project for 20 years to be now counting 20 days. 22 days, 21 days. It's really, it's pretty amazing. But I will warn you, when we launch, we're not going to get the pictures right away. You must wait. We will have to wait for the science. After we launch, it's going to take a month to travel from Earth out that 1,000,000 miles to L2. And then once we get there and to go into our orbit around L2, we're going to have 3 months of aligning all of those segments of the telescope that you see here. They're all separate segments. They all have to be carefully aligned. And then 2 more months aligning and preparing all of our equipment for science. So the first science will not come until July. So be patient, but it will come. All right, so let's wrap. What is James Webb Space Telescope? All right. The wrap here, you know now it is a new kind of telescope. It will see things beyond what Hubble can see because it's bigger, redder, colder, and further. How does it see? It sees with very large and complex cameras and spectrographs. What do we plan for Webb to see? First light, evolution of galaxies, the formation of stars and planetary systems, and many things within our solar system. And will Webb see God? I'm going to leave that as an exercise for all of you to ponder based on what I've told you today and what your personal understanding of God is. But even if it doesn't see the man in the sky, it will see amazing and beautiful aspects of reality that we have not yet had a chance to see. So thank you for listening. And what questions do you have? I'm happy to answer them.
Thanks, Heidi. That was just fabulous. What a wonderful talk. I'm going to encourage people that have questions to enter them into the Q&A. And I'm going to start out with a question of my own. I'm a biologist and I do X-ray microscopy where it's much the same. It happens at a national lab. I get my data at home. I play around with it. And so it works much the same. But when something goes wrong and there's a misalignment, I can send somebody to go fix it, or I myself can go and fix it. What do you do from millions of miles away when there's something that goes wrong with the telescope?
Right. So first of all, we try to build the telescope so robustly that nothing is going to go wrong. We also test this telescope 6 ways to Sunday before we send it off. I think many of you heard, if you're paying attention, recently something went wrong. The launch site's band was slipped, and so we delayed the launch for a couple of days. But we delayed the launch because we were checking everything that could possibly have happened when that event took place. You have to trust your crackerjack engineers that we have tested everything and prepared everything. And of course, we do already send spacecraft all over our solar system. And, when you send something out to Neptune, you can't send someone out to study it. So, or to fix it if something goes wrong, you work around it. So that said, if things happen that we are not anticipating or that we haven't planned for, we always have things in our back pocket. An example I gave someone recently was, We launched a mission to Jupiter called the Galileo spacecraft, and its main antenna only opened a tiny bit. All right. And so you didn't have your antenna open to send your data back. And so when something like that happens, what do? Well, you can jiggle the spacecraft. You can like try to move something so it imparts a little jolt. So if something's caught or stuck, you can do that. And so our team of engineers with Webb, they have plans that if something goes wrong, if something doesn't deploy the way they expect it to, they have a plan B, like how you're going to jiggle it, how you're going to rotate it, whatever. They have a plan B for the plan, a plan C for the plan B. They've got plans. So you just have to be very creative about how you do things, is all I can say, Gail. You can't, we don't have the capability of sending astronauts even to the moon right now, let alone 4 times the distance of the moon. But we could not put this telescope in low Earth orbit like Hubble. We simply couldn't put it there. You can't do the science there. And so,
Look, I think
it is what it is.
There are quite a few questions. First, just a comment. Don Fine said, I see God in everything that exists. It is his creation from the smallest particle to the large of the universe. So just to point that out. Larry Engelhardt asked, how long does it take for a star to be born? How can we see birth of stars or planets with snapshots from our telescopes?
Oh, yeah, thanks for that question. So it takes a long time for a star to be born out of the dust that surrounds it. So we can't ever see one individual star being born. But what we can do is we can look at many, many hundreds of stars, many of them in similar conditions, and we can determine the ages of the stars very precisely by looking at some of the chemicals that we see in their stellar envelopes. And so by building up a history of star formation, of different shapes of stars, sizes of stars, different environments of stars, we can create the storyline of how a star forms. And so one of the things we want to do with Webb is to fill in some of the gaps in the storyline because they're hidden inside those dusty clouds. And so while we won't be able to see an individual star go through all of the phases of its life, because that takes millions of years, by looking at many, many stars in similar environments, we can create that storyline. So I hope that, and the same is true of galaxies as well. Instead of millions of years, it's like billions of years. But that's how in astronomy we put together these stories for things that are much, much longer than human timescales. Oh, you're muted, Gail. Got to unmute. Yeah.
Just realized that. Question from Michael Hobbs. Can you talk about the most distant, oldest light that Webb will see, in quotations? How soon after the Big Bang is that light? What do you hope to learn from being able to see it?
Right. So we don't know for sure the answer to your question. And that's why I was being a little cagey. Some people say, yeah, you'll see the first stars that form. And other people are, and I'm a little, I'd rather undersell and over deliver. I'm like, I'm only going to promise the first galaxies, not the first stars. But what we're talking about is, if memory serves, it's something like 300,000 years after the Big Bang. So we're talking really early, right after, for those of you who are astronomers, right after the period of reionization, when the first light began to propagate in the universe. That is the moment that we hope to be able to capture with Webb. We expect that those earliest galaxies will be extremely rich in hydrogen. That is the most abundant thing, and that they may not even have gotten to helium burning yet, but that's the kind of question that we want to find the answer to. That's our hypothesis, that they're going to be what we call population 3 stars, hydrogen, just pure hydrogen stars. That's kind of what we think. And as to what the very first galaxies look like, that is why we're building this telescope. We can look far back in time with Hubble I don't know the exact numbers of the ages of these stars, but when we start looking further back in time with Hubble, looking into the deeper red images, these galaxies become less well organized, less spiral shapes, and more blobby and kind of bleh. And so, we don't really know what the very first ones are going to look like. So stay tuned. In about a year from now, you'll have an answer to that question.
Great, thanks, Heidi. Question from Maynard Moore. Maynard actually runs the IRAS seminar series. He's the vice president for IRAS. What is cosmological dust? Particles. What is the origin of this dust? Does it have measurable mass? Where does it go? Does it consolidate? Does it dissipate? Is it pervasive throughout the universe? Does this dust have any scientific value, or is it simply a barrier to clarity?
Is that a comment or a question?
No, it's a question. A bunch of questions, a lot of questions.
So yeah, dust is everywhere. And some of my colleagues spend their entire astronomical careers studying cosmic dust. Dust it is friend and foe. It is a friend because dust is that which creates planets. That the dust is where the planets come from. Everything that we see around us is made of cosmic dust. That whole Carl Sagan, we are all star stuff, as if we're the dust, that has come. But it's a foe because you get too much of it, you can't see through it, And so, part of building this infrared telescope is to be able to peer through some of the dust in the dustier regions in our local galaxy, so we can, get into those areas. But yeah, dust is everywhere, including under my couch, that's not cosmic dust, but, dust is everywhere in the universe. It's just a natural outgrowth of the birth of stars. They get to a point where they're so large that they just explode, and that material is just distributed throughout the universe. And that is the cosmic dust that is everywhere. So dust, it's a huge part of the story. A huge part of the universe's story is that dust. From dust you come, and to dust you shall return.
Okay, there are a series of 3 questions from an LSTC student, Eric Boss, that have been posted on the YouTube chat. The first one is, someday in the distant future, beings will have no evidence of the Big Bang due to matter accelerating away from each other. I guess that's a comment. But then he says in the second question, in the real question, are you concerned that these future beings will be trapped in a medieval view of their world with no evidence of the creation of the universe? Will their sciences develop differently?
That's a really interesting question. I mean, I'm sure we can write all sorts of interesting hypothetical stories about that. One might hope that that our species remains sentient long enough that we can transcend our Earth and our knowledge to be able to communicate information in a different way than our limited view right now. It's hard to imagine, and furthermore, we don't know whether or not there are other species out there somewhere in the cosmos that have also developed sentience as we have here on Earth. And so, I mean, it's a really interesting question you're asking. And, it's a little bit beyond the realm of an astronomer to answer that question. It's more a philosophical question about how does one know things about one's universe. So we know things using our brains and our senses, and we build tools that help us expand our senses, whether it is to see further or to probe deeper or to, learn in different ways. And so, maybe those far, far future, people will have different ways of sensing that will allow them to come up with the story of how their universe formed. But that's the best I can do for you right now.
Yeah, Eric has another question, but I think I'm going to come back to that at the very end if we have time, because there's so many questions that are piling up. John Otto Lilienstolp asks, quantum physicists tell us what we humans perceive as matter are pattern events that are being generated within a field of energy that embraces all that is. Some physicists hypothesize that this all-embracing energy field is a form of consciousness. Are you familiar with these hypotheses, and what do you think of them?
I think that they're very interesting concepts. You know, as a scientist, as someone who's been trained as a scientist, I really rely on observables and predictions, and particularly predictions that make things that can be observed. And so whenever confronted with new ideas or new concepts like that, the questions that I would always ask are, do they make predictions that we might be able to create a way of observing whether that prediction is true or not? And if the answer is yes, then it fits into our framework. And of course, Einstein's theories of general and special relativity are the quintessential examples of that. He made predictions that at the time that we had no way of checking if they were true or not. But as our technology developed, we could actually then go and say, oh yeah, actually what he said is true. You know, gravity, masses do distort space-time and bend things, and Einstein rings form, and I mean, there's many others. So, you know, I keep an open mind on interesting concepts like you're describing, and I wait for the predictions, and I wait for the means of proving them, because until then, it just stays a very interesting theory. And I'll put string theory exactly into that same category. By the way, it's just so we don't get a question about string theory.
Great. Trenton Farrow asks, how many universities and other entities and how many astronomers scientists will be able to access and work with the data from Webb? I've been watching programs from Arizona State University, which seems to have an intimate relationship with Webb.
Yeah, you mentioned in the introduction, I'm an interdisciplinary scientist for Webb. One of my fellow, there's 6 of us, one of my fellow interdisciplinary scientists, Roger Windhorst, is at Arizona State University. And so they do have a very big program with Webb right now. Webb is what we in astronomy call a great observatory. It is open to all. People must write proposals saying what science they want to do with Webb. And those proposals, once a year, they're all collected, they're taken and evaluated by astronomers. We do it with a process called dual anonymous. So the people reviewing it do not know who the people are who are asking to use the telescope. But they just review the science. Is this good science or not good science? And they rank them. And the ones that are good science will get time. Ones that are not good science, you know, they get a very nice letter saying, thank you very much. You need to work on this part of your proposal to make it better next time. And so we got over 1,000 requests to use Hubble for its first cycle of observations, its first year of observations. And not all of them are selected, unfortunately, but you can go online and you can see who got the time, and there's dozens and dozens and so it was like, I don't know how, I wish I knew that off the top of my head. I should know it, but I forgot how many proposals are actually going to be getting time on Webb. We do the same with Hubble, by the way. You know, you propose to use Hubble, and if you write a super great proposal, you'll get the time to use it. So they're open to all astronomers who have great ideas, and that's the most meritorious, democratic way that we can use these facilities.
And in a kind of related question, can the Webb telescope record sound and video, or only still images?
The Webb telescope takes images and spectra. That spectra where you break the light into a rainbow of colors and you record all the different colors. You can take many, many pictures and make them into a video. We don't get any sound. People have been doing what they call sonification of images, which is very interesting. If you like Google sonification Hubble image, you will find examples where people take those two-dimensional images and then they turn them into sound. And it's very interesting because our human brains perceive sound in a different way than we perceive light. And sometimes you can hear stuff in your data that you don't see. So it's an interesting concept. But we take pictures, we take black and white pictures through different filters, and then we combine those different black and white pictures to get the kind of color pictures that you see coming out of Hubble. And we'll have many, many beautiful Webb pictures as well. People ask me sometimes, just to cut off this question in case it comes, well, it's an infrared telescope. How will you be able to get pictures? Well, just a pro tip, a lot of the Hubble pictures you see are actually ultraviolet and or infrared. We just turn them into colors on the computer that your human eyes can see. So we will have lots of fabulous pictures. And the way we get movies is we just digitize, we use the digital information and turn it into movies depending, it depends on what you're trying to illustrate in the picture. So
great. I'm going to make this be the last question. There are a lot of comments in the chat that we'll make available to you. Jim Miller asks, one of the quests for astrobiology is the discovery of a second Eden, a presence of life independent of Earth. One of the Webb's missions is the search for life on distant planets. Were such life discovered, what would be the theological import?
Yeah, I think you should have asked one of your last speakers of that you should have asked Dr. Guy Consolmagno, director of the Vatican Observatory, that question. He's written a whole book about that. Would you give communion to an alien? I'm not a theologian, so that question is a little bit out of my bailiwick. I will just share a few points about the question. First of all, Webb was really not the tool that was designed to search for life on other planets. The kinds of planets that are most amenable to James Webb Space Telescope are going to be large planets like Jupiters or Neptunes, and they're going to be large planets that are close to their host stars. So they're going to be hot Jupiters or hot Neptunes, not really amenable to life as we know it, where there's liquid water. The one exception to that is planets that are around small, cool stars that we call M dwarfs. Because those stars are small and cool, then the planets that are near them, they're easier for us to find. We've been able to find Earth-like planets, or what shall we say, Earth-sized planets near the M dwarfs that are at distances where liquid water might be on their surfaces. So for those of you who are exoplanet aficionados, the TRAPPIST-1 system that has 7 Earth-sized planets, several of which are in what we call the habitable zone, that's going to be a key target for Webb. But the holy grail for us, for exobiology, is to try to find an Earth-sized planet around a sun-like star. And right now that is a little not within the grasp of Webb. We don't know of a system like that close enough to us for Webb to be able to characterize it. So we are thinking about what telescope do we truly need to do that? And the astrophysics community has just released what we call a decadal survey. And one of its top recommendations was to build a new telescope, kind of like a super Hubble, like, as large as Webb, but with the capabilities of Hubble. And that would be the tool that we would really need to characterize dozens of Earth-like planets around sun-like stars, look at those spectra, and see if we can find signs of chemistry that are indicative of life on those worlds. So it's a really exciting time for us in this field. We are at the point as a species where we may be able to answer this question: are we alone in the universe? We are at the cusp of that, not only around planets around other stars, but whether maybe in the subsurface ice on Mars or under the icy crusts of Europa or Enceladus or Triton, we are at the point now where we can maybe answer this question. And there would be a lot of interesting theological implications, but I'm not qualified to address what they would be.
Thank you, Heidi. This has been so fabulous. I mean, I think it's one of the most timely talks we could have had, but your enthusiasm carries over to everybody. And the fact is, the comments are just amazing. Everybody has really enjoyed this session, so I want to thank you. There are a lot of questions in asking about whether this is going to be available. The webinar, it was streaming on LSTC's YouTube page, will be available there shortly after the webinar ends. And I do want to note that Heidi told us before this started that her mother attended LSTC. So for those of you who are students or faculty who are participating, there's a way in which Heidi's part of the legacy of LSTC too. And Grace, it looks like you want to have a few closing comments.
Just one final question for Heidi. First of all, that was a spectacular talk. Thank you so much. I would personally like to know, and I bet everybody else who's still tuned in would like to know, what you find most exciting, what science. I mean, this is perhaps not fair because there's so much extraordinary science that's going to come out of JWST, but is there any one question in particular that you're pursuing that you would like JWST to provide insight on?
Well, of course, you're asking me like, which of my children is my favorite? I love them all. And I'm very excited about all the science that is going to come from Webb. I became involved with Webb years and years, decades ago, because I really wanted to understand the atmospheres of the giant planets Uranus and Neptune. And so I've given away all of my guaranteed time. And so there's a team of much younger scientists who are going to be doing those observations. So I'm going to be watching to see what they learn about Uranus and Neptune. But I got to tell you, I'm just as excited about the first light in the universe. And I'm also excited about what we're going to learn about planets around other stars. By the way, we didn't even know about them. We didn't know they existed when we started building Webb, and now there are, almost 5,000 known planets around other stars. And so, it's a whole new world out there for us to explore. So I'm just waiting for all of it. What can I say? It's going to be amazing.
Thank you.
Great. Thanks so much, Heidi. Thank you, everybody, for participating, and we'll send you information about our next CASIRAS webinar as it pops up. Thanks, everybody.
Thank
you. I'm going to ask LSTC support to come up with a way to send you the comments. A lot of questions came in the comments, not just in the question box. And there were a lot of just very nice, I loved this, I love what you did, or when you're talking about space dust, somebody puts in ashes to ashes, dust to dust, a little bit of humor there. I mean, so I'll see if we can come up with a way to send it to you. Okay.
Thank you. That would be very nice. So
and thank you so much. I myself, I'm a biologist, not astrophysicist, but you got me excited. So that's great.
Good. That's good. Thanks.
Thanks so much, Heidi. That was really masterful science communication and just so much full of wonder. I really appreciate it. Love the way you navigated the theological and spiritual questions too.
Yeah. I didn't know how I was going to handle that. I had to really think hard about that.
Very evocative. Really, really nice.
Yeah. Thanks for presenting.
Yep. Good night, everybody. Everybody have a good time.